Hello everyone. In today's lecture, we are going to conduct an experiment on measurement of gain and directivity of antennas, which is seventh experiment in your communication laboratory. Contents: antennas, antenna parameters, polar plot, and then demonstration. So basically, first we have to learn the theory behind this experiment. Then we can move on to the demonstration and also some of the measurements which we are going to do in the practical setup. So what is an antenna? Antenna is a conductor and it is a transducer which acts as a facilitator for wireless communication. You can consider an example where there is a FM radio station. There is a FM radio station which will have a large antenna which will broadcast the signals, and you will be having a radio set which will receive these signals. Correct? So here this radio set will also have an antenna which is called as receiver antenna, whereas the FM station is having an antenna called as transmitter antenna. So first it is acting as a facilitator for the wireless communication. Physically it is a conductor. Logically it is a transducer. What it transduces? It transduces electrical signals to electromagnetic waves, or converts electrical signal to electromagnetic waves at the transmitter end. At the receiver end, electromagnetic waves to electrical waves or electrical signal. So an antenna radiates EM waves and or collects them. So as a transmitter, it radiates the electromagnetic waves. As a receiver, it collects them. Sometimes same antenna can act as a transmitter as well as receiver. So it can radiate as well as it can collect the signals. Okay. So at the transmitter end, the radio transmitter supplies an oscillating radio frequency electric current to the antenna's terminals, and the antenna radiates the energy from the current as electromagnetic wave. So as indicated at the transmitter end, electrical signal is converted into EM wave and it is radiated into the space. At the receiver end, antenna collects incoming electromagnetic waves and convert them into an electrical signal. So how this radiation mechanism works? It basically works on the flow of current. The same has been explained here. When electric charges undergo either acceleration or deceleration, electromagnetic radiation will be produced. Hence, it is the motion of charges, that is nothing but current, is the source of radiation. Okay, so elaborate discussion on this might have been done in the MWA course. Correct? So we'll not go into in-depth details of this. So only thing is when electrical charges undergo acceleration or deceleration, radiations or electromagnetic radiations will be produced, which will propagate through the space. Another point to note over here is the electromagnetic waves travel with the speed of light, that is c is equal to 3 into 10 to the power 8 meter per second. This is the speed of EM waves as well. That means these EM waves travel any place on earth within no time. So within no time it can reach out any corner of the Earth. The next concept we need to know while discussing antennas is radiation pattern. So, what is an radiation pattern? An antenna radiation pattern is defined as a graphical representation of the radiation properties of the antennas as a function of space coordinates. So it is clearly defined over here. It is the graphical representation of radiation properties of antennas as a function of space coordinates. So XYZ coordinates you can consider. Using these coordinates, we graphically represent radiation properties of the antenna. So this figure shows the radiation pattern of an antenna. As it's been already explained, is the graphical representation of the radiated power or received power. So the main direction or the direction in which maximum power is transmitted or received will constitute an area called as main lobe. So with this angle the power is being radiated or received and which is maximum in this direction. Okay, and it is known as main lobe. Likewise, we have side lobes which lies beside the main lobe and back lobes which are exactly opposite to the main lobe. And the power you can see side lobe and back lobe powers or power levels are very low as compared to the main lobe power. And the maximum power of the main lobe is denoted as 0 decibels. So this is our reference, and at the half power point, that is minus 3 dB, if we draw a line and join the origin points to this line, that is intersection of the line, then we will be able to measure the half power beam width. So this is 0 decibels, whereas this is minus 3 decibels. If we draw the intersection lines, already they have been drawn, and the angle if we measure the angle between these two lines, then it is half power beam width for the particular antenna for one plane, that is E plane or H plane, and the angle between the first nulls is known as full null beam width or first null beam width. So nulls means the power radiated or received is minimum or lowest. So between these two nulls, if you measure the angle, it will be full null beam width or first null beam width. So using this half power beam width, we are going to measure gain and directivity of different antennas. So in our experiment also, we are going to plot this radiation pattern, and using this radiation pattern we are going to find out half power beam width for the particular antenna, either it might be dipole or Yagi, and then use this parameter for E plane as well as for H plane to calculate gain and directivity of the antenna. Okay. Next, coming to the important topic, that is gain and directivity of antennas. So what is directivity? Directivity is the ratio of power density in a certain direction to the total power radiated. So if you consider this diagram, the dotted lines, this is power density in particular direction, whereas power density over entire area, if you consider this power this power as well as this power, the dotted lines, all you have to consider. So the ratio of total power, sorry, the ratio of maximum power in the particular direction to the total power which is radiated. There is a slight radiation in other directions also that we'll consider, and we'll make a total power. It might be like maximum power might be say 4 decibels, whereas 3.43 decibels might be, sorry, 4.43 decibels might be your total power. So what is this 4.43 decibels? It is the power in the side lobes, so which will be considered to be a loss, kind of loss. Okay, because we want maximum all the power to be radiated in a particular direction in some of the applications, not always, but in some of the applications. Okay, so that is the meaning of directivity. In certain direction we want maximum power to be radiated, and directivity is defined by the power density in a certain direction divided by the total power radiated, which is given by this equation. As you can see, d is equal to 4 pi, this is solid angle, multiplied by maximum radiation intensity U max by power radiated. Okay, now coming to the gain. What is gain? Gain is the ratio of power density in a certain direction to that of total input power to the antenna terminals. So gain is power density in a certain direction divided by total input power. Okay, so you can clearly observe the difference. Input power is different and radiated power is different. Why? Because input power might be 1 watt, radiated power might be only 0.8 watt. Where is the zero point 0.2 watt? It is dissipated or lost in the process of the signal conversion. And this gain is defined by another equation, which is this one. Gain is equal to antenna efficiency into directivity. So this antenna efficiency is the indicator to represent how much of electrical energy gets converted into electromagnetic energy. This is a kind of energy conversion ratio. So what it indicates? It indicates the efficiency. As I have told, if you have transmitted 1 watt of power, you have fed 1 watt of power, if 0.8 watt only getting radiated, its efficiency is 0.8 or 80%. So gain is always lesser than directivity. That is what the meaning. Because efficiency may not be greater than 100, right? It should be lesser than 100. You have to multiply a fraction with d, so gain will be always less than that directivity. That's why you can see gain is less, because gain involves the or considers the losses. Gain considers the losses in the antenna. Another important term I left without explaining is isotropic pattern. What is this isotropic pattern? You must be knowing, right? You can see in every direction equal energy is being radiated. An isotropic antenna or an isotropic source can be used to radiate same energy in all the possible directions. And you also need to remember this isotropic antenna is an ideal antenna or ideal source which is not there in existence. Okay, we can model some of the very important concepts of antennas using this isotropic pattern. That's why we use this is a standard. With respect to this isotropic source, we compare our other antenna and their patterns. Okay, so that's about the gain and directivity. The point you need to remember is if antenna has ohmic losses, then gain is less than directivity, which is the practical case always. Directivity will be higher because it does not consider the losses, whereas gain considers the losses, and thereby it is efficiency multiplied by directivity. Next, types of antennas. This is also very important. We have number of types of antennas, which is in terms of the applications, in terms of the dimensions, in terms of the distance which the signal has to be traveled, in terms of the reach or the area which has to cover, the application in which it can be used, whether it is satellite application, whether it is for television, whether it is for FM radio, AM radio, short waves, whether you are going to use it in on top of the car or any other vehicle. So based on this, different types of antennas we can name. Few of them have been explained here. So monopole or whip antenna, dipole antenna, loop antenna, Yagi or Yagi-Uda antenna, and this is dish antenna. This is to just familiarize different antennas. Okay. Now we have come to our topic of interest, which is microstrip antennas. In our lab, we are going to find directivity and gain of microstrip dipole antenna and microstrip Yagi Uda antenna. So Yagi Uda are the names of the scientists who have designed these antennas. So what is dipole antenna? This one. This is wired dipole or metallic dipole. Instead of that, we are going to use microstrip. So I will explain that. Then this is Yagi antenna. Microstrip version of this Yagi is microstrip Yagi antenna. Okay, these two antennas we are going to study, where this is a low gain antenna, whereas Yagi antenna, which we have seen on the on top of our homes for television signal reception. It is not the only application. There are many applications of this Yagi antenna because it is a very high gain antenna. So these two antennas we are going to examine for gain and directivity. That too microstrip. So what is microstrip or a patch antenna? Microstrip patch antenna consists of a radiating patch on one side of a dielectric substrate, which is usually FR4, that has a ground plane of Cu on the other side as shown in the below figure. So you can see in this figure, this is ground plane, this is substrate, whereas this is the microstrip patch. Okay, so patch means it is just a strip, or it is fabricated on a PCB board, which you can see over here. So this is array of 4x4 patch antenna, which is going to have a frequency resonance of 10.3 gigahertz. The same kind of patch antennas are used in your mobile phones also. Okay. So another point to remember is microstrips are used in aircrafts, spacecrafts, satellites, missiles, cars, and mobile phones. So, range of applications we can expect from these microstrip antennas. So, as I have told, the microstrip version of Yagi antenna and dipole antenna we are going to use and measure their gain and directivity. Okay, so you can see in the figure, the first one is Yagi antenna, the second one is microstrip dipole antenna. Before we move to the demo part, let me say another important topic, which is about polar plot. This is the plot which we use to plot the radiation pattern and then determine half power beam width and use it for calculating gain and directivity. So this is the plot where we can draw our radiation pattern like this, for example. Then if this is our 0 dB minus 3 dB line like this, and then we'll draw the intersection points and then measure this angle and say it is for theta E in the electric field. For the magnetic field it will be theta H. You can draw on the other side, and using these you can calculate the gain and directivity theta E and theta H. Okay, so how to plot this radiation pattern and measurement of half power beam width, we'll see in the next video. Okay, so first we'll complete the demo, then we'll come back again. After demo you will be conducting the experiment, and you will be knowing the radiation pattern or the power radiated or received by the antenna for various angles. So we can do this once we complete with the experiment, correct? So let us now move on to the demo part of this experiment. In experiment number 6, we are going to measure the gain and directivity of two microstrip antennas. One is Yagi antenna, which is the one I am holding now, and next the dipole antenna. Okay, for these two antennas we are going to measure the directivity and gain. Okay, so the procedure is like this. Initially these antennas are designed to radiate at frequency 1.25 gigahertz. So we will set our frequency in the microstrip antenna trainer as 1250 megahertz, that accounts for 1.25 gigahertz. Okay, that's why first we'll set the frequency, and then using the probes we will directly connect the signal from input to output, and the connector I am using is SMA connector. Okay, now you can see the power level is indicated as 104.9 dB microvolt. It is the transmitted power, you can say VT is equal to 104.9 dB microvolt. Okay, now once it is measured, it can be used throughout your experiment, that is for Yagi antenna as well as for the dipole antenna. Okay, now once you measure this, remove the direct connection, and now you have to connect the signal to a transmitter antenna. Okay, this is our transmitter. It should be inserted like this for E field measurement. Now at the receiver end also you can see there is another antenna which is of same type, that is Yagi antenna. So both are symmetric. You can use this one as transmitter, this as receiver, or this as transmitter and this as receiver. Once you firmly fix this, now you have to insert into the position of this antenna stand. Okay, this is our receiver, because the receiver is the one which is going to vary in its direction, and we have kept our antennas by 50 centimeter apart. Okay, approximately, because 6.75 centimeter is the far field for this antenna which is calculated. That's why we'll have to keep more than 6.575 centimeters apart, okay, for far field region. This arrangement is for electric field measurement or the theta E measurement of the beam width. Now if you want to measure theta H, then the arrangement should be like this, or using the other bend which is here. In this way you have to fix the antenna, okay. This is for H field measurement or theta H. So coming back to the theta E measurement only, I will explain you the procedure how to measure theta E. For theta E measurement, this is the arrangement as explained earlier. Now this receiver is in the line of sight. The transmitter and receivers are in line of sight. At this point, whatever power we are observing, that is 86.7 dB microvolt, is our VR for this antenna. VR is the received voltage level, or in microwaves we say power level. It is 86.7 dB microvolt. Okay, so VT is 103, around 103 dB microvolt. VR is 86.7 dB microvolt. Now we have to measure the radiation and note down in the tabular column. So here first we have kept our antenna at 0 position. You can see the position over here, it is at 0 degree. The corresponding value for 0 degree is, the power level is 86.2 dB microvolt. Now in clockwise direction I will rotate by 15 degrees. This is the clockwise direction where I have kept my antenna at 15 degree. So corresponding reading is 85.2, okay, around 85.8 it is, okay, 85.8. Now further I will rotate by 15 degree. I will take the reading at angle 30. It is around 83.7. Similarly, I have to rotate it to 45 degree and corresponding power level will have to take it as a reading, and then 60, then 75. You can observe the change in power level or the radiation received by the antenna, and then finally up to 90. Okay, so at 90 you are getting around 65 dB microvolt. That is the maximum radiation you are getting. So this is for positive angles, the clockwise rotation of this receiver. Whatever the value we have got, we have to write it for positive angles, positive power. Okay, that is just an indication. Now same thing is repeated for anti-clockwise direction, that is 0, 15, 30, then 45, 60, 75 and 90. Okay, in that way you have to take down the readings from 0 to 90 degree in clockwise and 0 to 90 degree in anti-clockwise, and corresponding power values you have to write down in the tabular column for theta E. This is for theta E. Now for measuring theta H, as said earlier, you have to replace the position by this one. Okay, this is for theta H measurement. You can see again we will have to take reading from 0. For 0 degree, what we are getting, the power level as 73.2. Similarly, let me adjust this. Similarly, you have to rotate in the clockwise direction. For 15 degree, whatever power level you are getting, that you have to write down. Next 30, next 45, next 60, 75 and 90. Corresponding power levels you have to write it down, okay, in this way. And then come back to 0 again and rotate in the anti-clockwise direction and take down the corresponding readings in the negative angle and negative power columns, okay. That completes your reading. Once you take the readings, you have to put the polar plot and then you measure theta E and theta H, because your half power beam width need to be calculated. Once the half power beam width is calculated, you can calculate directivity and then you can calculate gain. And the experiment is repeated with dipole antennas. Here we are using Yagi antenna. We have taken the readings. The same experiment can be repeated for dipole antennas by replacing the antennas.